slide to start, but I wanted just to make the statement. And now let me illustrate. So let me illustrate the physics of this using this video. This very nice video that Douglas Ashton made to explain the physics of the Ising model. Okay, so it's a 1-minute video. Let me guide you through it. Well, it's not very important to read now. I will explain. So let me first stop it. Okay, so we have three pictures. Let me even start from the beginning. We have 3 pictures, which are 3, if you want, photos of a typical configuration of the Ising model at 3 different temperatures. Okay, so in the middle is temperature exactly equal to the critical temperature, T equals Tc. On the right, you see T slightly bigger than Tc. You see it's like 0.3% higher than Tc. And on the left is slightly below Tc. And in the picture, you see white dots correspond to spin up and black dots to spin down. Okay? So it's just a way to show the configuration. And so you see that originally the 3 pictures look the same because, well, it's so close to the critical temperature that you don't notice the difference. But now what the movie is going to show is the process of zooming out. Okay, so you're going to look at the system at bigger and bigger scales. Okay, so this is what is happening here already on the left. You're zooming out. And this process of zooming out has a very technical name in physics. It's called the renormalization group. Okay, so this is called the renormalization group flow, is a name for zooming out. Okay, now you see zooming out at high temperature, what happens? And then you will see what happens when you zoom out exactly at the critical temperature. Okay, so when you zoom out exactly at critical temperature, this is what happens. Okay, so I hope it was clear. So I wanted to stop it here. Okay, so let me just comment on what we saw. Many of you probably already saw this picture, but I guess for the newcomers, let me just explain the basic physics that we just observed. Okay? So let's first look on the left, okay, like the order we saw. So that's temperature slightly below the critical temperature. So as you zoom out, you start to see, so let's say white is spins up, you start to see that most of the spins are actually up. And there's only a few black dots if you go to very, very, very large scales. Okay? So this is the basic signal that there is a finite correlation length. You can think of the correlation length as the typical distance between neighboring black dots, okay, in this picture on the left. And you see that it's finite. Then on the right, you see the opposite. On the right, you see that because you started slightly above the critical temperature, as you zoom out, you see that the non-trivial structure that was there at short distances kind of disappears, and you just see a random black and white dots. It's like the picture is more or less equivalent as what you would get if you do the simulation with independent spins. Each spin can be up or down with probability a half independent of the others. Okay, so this is like infinite temperature. But in the middle, you see something more remarkable. In the middle, you see that nothing changes. Okay, so if you actually look at the middle movie again, you see that it's zooming out, but you cannot distinguish. If I stop, you cannot tell me, this is zoomed out and this is zoomed in. The system is what's called scale invariant. If you look at any scale, you see there are some changes, but the statistical properties are always the same. And that's the signal that the correlation length is infinity. And so this scale invariance it actually leads to some special type of quantum field theory. If you are exactly at t equals tc, this quantum field theory will be scale invariant, and that's what we call a conformal field theory. Okay. So let me go back to my presentation. So the statement I want to make is that quantum field theory describes the neighborhood of the critical point where the correlation length is much bigger than the lattice spacing. If you sit exactly at t equals tc, that's actually a special quantum field theory, is a conformal field theory because it's a scale invariant quantum field theory. Okay, and well, maybe this equation is not so important, but sometimes you will see that we often write the system like that. We say that the quantum field theory action, if you want, like the theory for quantum field theory, is the theory for t equals tc, which is the conformal theory, plus a small deformation proportional to t minus tc. Okay, and this, we call it a relevant deformation. So this is a very important technical term, and we just saw it in our eyes. Why is it a relevant deformation? It's because when we zoom out, its effect grows. So although you started very close to t equals tc, when you zoom out, the aspect of the system is completely different than if you start at t equals tc. So this small deviation is amplified by the renormalization group flow, by the process of zooming out on the system. Okay, so here I'm showing you a nice figure that, well, we always plot in quantum field theory, which is a figure where we think of energy as the going up. And as you know, in quantum mechanics, energy and length are opposite, right? The wavelength, the bigger the wavelength, the smaller the energy, and vice versa. So zooming out is going down on this picture, is going to lower energies. And we often say that a quantum field theory is starting from a conformal field theory, which is this theory at t equals tc, and then introducing a very small deformation, and then zooming out, doing this process. And then, well, you can end up either in other conformal field theory or just in this trivial state that we saw. But okay, this is not very important. I just want you to, yeah, this picture is something that you will probably see if you ever study quantum field theory. And the idea is rather simple. Questions? Any question about this?
Feel free to unmute if you want to ask any questions. I think you should be able to do so.
Okay, so this is one, yeah, you just keep this in mind. Well, if you know statistical physics, I guess you understood what I said. You know most of it is standard course material. But if you don't, just keep this in mind that lattice systems at continuous, when you have a continuous phase transition and the correlation length is much bigger than lattice spacing, allow you to define a continuum limit, and that's what a quantum field theory is. Okay? And this is the best mathematical definition we have at the moment, okay? In particular for quantum chromodynamics. Okay, so now I think it's time for the intermezzo. So I want to tell you a bit about harmonic oscillator in quantum mechanics, an harmonic oscillator. Okay, I'll stop for 3 more seconds so that you have time to ask me a question before I change topic. Okay, so quantum mechanics. So this is the standard harmonic oscillator at frequency omega, so a particle moving in a quadratic potential. And this is how you solve it, right? So this is review of your quantum mechanics 1. you just introduce creation and annihilation operators, A and A dagger, and the Hamiltonian becomes just A dagger A with these standard commutation relations. And therefore, the energy levels, so the eigenstates of the Hamiltonian, they have a discrete spectrum, and the energy levels are just h bar omega times a half for the ground state plus integers for the excited states. Okay, so this is the standard harmonic oscillator. It has a very simple analytic solution. So now, what happens if you add a quartic term, right? So this is what's called the enharmonic oscillator. Well, there's many types of enharmonic oscillators, but let's look at the quartic one. So what can we do in this case? Well, first of all, let me just rescale the variables. Okay, so this is a trivial rescaling. So I just rewrote this equation. I divided the Hamiltonian by h bar omega to make it dimensionless. And I defined a dimensionless P and dimensionless X and a dimensionless coupling so that I don't have to carry all these numbers, okay? So this is trivial algebra, but let me do it because it just makes the problem clean, okay? So now from here on, my Hamiltonian is this dimensionless Hamiltonian where, well, I can always go back by following the rescaling, but let me work with this one where all the variables are dimensionless. Okay, so this is a trivial rescaling. So now once you have that, the thing you learn in quantum mechanics is to do perturbation theory. You can say, well, let me treat lambda to be a small parameter and compute, for example, the ground state energy as a series expansion in lambda, right, in the enharmonicity parameter. So it starts as a half from the harmonic oscillator. So recall that here, yeah, h bar omega was factored out. I'm working with the dimensionless version of the Hamiltonian. So you just have this series, okay? Lambda square with coefficients. And here I'm showing you what these coefficients are. Actually, I will show you in a few minutes a code to compute all these coefficients, okay? So that you can play with it. So for example, the order 10 coefficient is this interesting rational number, which is of order 10 to the 10. In fact, so Bender and Wu in 69, they studied this series up to, I think, order 75. And they showed that the large order behavior of these coefficients is like that. So it grows factorially. Okay, this gamma function, remember, is more or less like factorial. So it grows with n very, very fast. Therefore, this sum that we were trying to calculate, we said, okay, let's calculate the ground state energy as an expansion in lambda, is nonsense. I mean, this series has zero radius of convergence. The coefficients grow factorially, so there is no value of lambda for which this series converges. Okay. This even the first year students should understand from their Taylor series calculus 1 that if you have a series whose Taylor series with these coefficients, they grow faster, they grow factorially, so that makes the series divergent, right? Okay, so that's a problem, and there are many solutions to this. So first of all, let me say that pragmatically, if lambda is really small, you can just keep a finite number of terms, the first few terms, and that's okay. That's a very good approximation. You cannot get arbitrary precision. If you want to get more and more precision, if you start adding more terms, at some point the series diverges, so you cannot. Then there are other tricks like Borel resummation, okay, but I don't want to go into that. But these tricks basically really work well if you have access to the entire series. So in quantum field theory, this is very hard, it's not accessible. So I want to tell you another way to solve this problem. Okay, so how to compute, I mean, there are many ways, this is quantum mechanics, so we know how to do it, but I want to tell you another way which is useful in quantum field theory. So this way is called Hamiltonian truncation. So the idea is extremely simple. So we take our Hamiltonian, again, the dimensionless version for making formulas cleaner, and we still introduce these nice creation annihilation operators for the harmonic oscillator. And so this is the result. So the Hamiltonian is now written as the harmonic oscillator part plus this deformation. Okay, so this is H0 plus lambda V, the standard form of Hamiltonian to do perturbation theory. But now we don't do perturbation theory. What we do is the following. We take the first n states of the harmonic oscillator. Okay, so take the eigenstates of H0, the harmonic oscillator, and build an n by n matrix, just with the first n states. And then just diagonalize an n by n matrix. Okay, that some computer can do very well, diagonalization of finite matrices. So then you get the eigenvalues of this finite matrix, and then you take the limit, so you compute for different sizes of this matrix, and you see that they converge to the exact value as n goes to infinity. Okay? Any question about the idea? I wanted to show you how this is done in practice, because I think you guys are here to compete and to learn how to compute. So I wanted to share with you actually how this is done in practice, just very quickly. But if you have any question in the meantime, please go ahead. Okay, are you seeing my screen?
Yeah.
My new screen? I changed now from one to the other. Is it working?
I think so, yeah.
Okay, so this is, well, how many of you work with Mathematica, the program? You can raise your hand just so that I have an idea of how many people know how to work with Mathematica. Okay, so for the people that work with Mathematica, this should be easy. It's just an implementation in Mathematica. Only 2? Wow. Okay, so I'm promoting Mathematica more. No, a few more. Very good. Okay, thank you. So let's see how this works. So I want to, as I explained, I want to compute this series. Do you see my cursor also?
Yes. Yeah.
Perfect. So I want to compute this series, and Bender and Wu, they came up with a recursion relation, which I just implemented here. Okay, so these lines of code implement this recursion relation. And actually, I'm pretty sure you can do better, because my collaborators often say that my programming style is agricultural programming. So I'm not the sharpest programmer. So I'm sure you can do this better and faster. But I just wanted to show you that with this recursion relation that Bender and Wu came up with, you can just, like, I'm running this in real time. So you see, for the first 10, I can show you the first 20 is like instantaneously in my laptop. And you see that the A20 is this gigantic rational number, which is 10 to the 26. Okay, so that's, you get this data. So Bender and Wu got to 75 using the best computers of the time, and they did not get to rational numbers because they had to work with machine precision, the best they could. But now with our computers we can do a lot. So here I want to show you that basically something they did is that now here I'm loading up to 85, because if you want to compute up to 85, it takes a few minutes. So I did it before. It takes like 3 or 4 minutes. And here is the asymptotic formula. And here I'm showing you the ratio. Okay, so the ratio approaches 1. So this asymptotic formula indeed works. You can check everything numerically. So for example, here for 85, the exact result is 4.74, and this one 4.8, 10 to the 167, a gigantic number. So this is the perturbative part you can play with. And here I did the Hamiltonian truncation. Okay, so here you have this Hamiltonian truncation, and And here is the matrix. Let me show you the matrix of the Hamiltonian. So here is for, if I take the first 10 states, this is the matrix. You see that in the diagonal, you have, so if you set lambda to 0, I can even set it here, lambda to 0. Lambda to 0. If I set lambda to 0, I just have the diagonal of the harmonic oscillator, a half, 3 halves, okay, a half plus integers. And if you introduce the perturbation, because you have a plus a dagger to the fourth, there are some off-diagonal elements, and that's how the matrix looks like. Okay, and now we can just ask Mathematica, compute the lowest eigenvalue of this matrix. Okay? For a fixed value of lambda, Mathematica is very efficient. So that's what this function does. And here I'm plotting. So here you see it also, I'm running everything in real time to show you that it's really fast, that you don't have to go to a computer cluster. So this is if you just do the matrix one by one. So you get this line. So this is the ground state energy as a function of lambda. Then this is 3 by 3. Then this is 7 by 7, 9 by 9. You see, it's already converging. So here it's still not, but for lambda equal 1, you cannot distinguish 7 and 9. But it converges super fast. It's actually exponentially fast in n. Okay. And here I'm showing you the comparison. So I'm plotting here. Let me show you already the final result here. I'm plotting here the, this one took a bit longer because I put 20 by 20 and I put many points. So here I'm showing you the exact result, not the exact result. Well, at this level of precision, this is the exact result, but these black dots were computed with Hamiltonian truncation. So this is what the ground state energy is. I'm doing 20 by 20, so up to lambda equal 1, this is already more, I mean, the error is much smaller than what the human eye can see. So this is the right curve. And then here I'm showing you the curves using perturbation theory at different orders. Okay, so like this one is a half, this one is like first order, 1/2 plus 3/4 of lambda. And you see that perturbation theory never really approaches the black curve if you want lambda, I mean, close to 1. It's like never, how many orders you put, it just gets worse. So perturbation theory is very good for very, very small lambdas. And this is what's called an asymptotic expansion. Okay, when you have a series with finite zero radius of convergence, you get an asymptotic expansion. It works very well here, but at any finite value of lambda, the series actually diverges. Okay, so I'm happy to send you this notebook so that you can play with it and improve it. I'm sure you can improve it. And yeah, I can send it to the organizers and they can share it to you if you want. Any question about this?
I think everyone.
Are strong coupling expansions any better?
Sorry, can you repeat the question?
I was wondering if strong coupling expansions are any better.
Right. Right. There is also a strong coupling expansion that you can do, assuming, but I don't think, well, I don't know enough. I think in the harmonic oscillator, you can get like the asymptotic behavior at large lambda that you can even get basically by dimensional analysis. But to get the systematic expansion as 1/lambda, I don't think it's very easy because the starting point would be just pure quartic, and that's also hard to solve. So okay, maybe you're asking me just if the function has a finite radius of convergence around lambda equal infinity.
Yeah.
No, that I don't think so, because the full complex plane of the function, so the function as a function of lambda has a branch point at lambda equals 0, and there is a cut that goes all the way to lambda equals infinity. So both points are singular, so you don't have finite radius of convergence.
Okay, thanks.
Okay, so I'll stop sharing here. Okay, let's see. I hope this works better now. I think it will. Let's see. Okay, you do not ask many questions. Okay, so this was the finish of the intermezzo, and now I want to talk about the particle physics perspective.
Actually, can I just ask a quick question before you go? I have one more from an experimental perspective. You talked about, I think most people, at least who've had a quantum physics course, will be familiar with the harmonic oscillator. You talked about the anharmonic oscillator. I was just wondering if you could briefly comment on what kind of real-world systems are actually modeled by this or can be modeled by this.
Well, that's right. That's whenever. Well, I will talk after in terms of particle physics. So whenever there are interactions between the particles, that's basically means that the analog of anharmonicity in that oscillator language. But more, I mean, more directly connected to oscillators, it's basically whenever you have some nonlinearities, right? So even in like cavities, right, of light cavities, that if you have some nonlinear element, like some material that doesn't respond linearly to the applied electromagnetic field, then that will give you some nonlinearity. And this, well, I mean, nonlinearity in the force is the mean. So linear force means the potential is quadratic, right?
Yeah.
That's what harmonic means. Once the forcing is nonlinear, it means the potential is higher than quadratic, so it's already anharmonic. So any kind of nonlinearity, I mean, also mechanical systems, as long as you have some correction to linear behavior, it will be anharmonic. I don't know if you have some more interesting experimental system in mind.
No, just, I mean, I'm coming from a solid state background, so I was thinking in terms of lattice vibrations, but exactly what you said, nonlinear terms, yeah.
For example, yeah, lattice vibrations would also be a case of that. Yeah. So yeah, for small vibrations, you can think, you can expand the minima, the potential around the minima, and so you keep just a quadratic approximation. But then if it vibrates a bit more, you will have also the next terms, the cubic and the quartic and higher, and that's anharmonic effects are important. Yeah.
Okay, thanks.
Yeah, in fact, they are very important to thermalize, because otherwise modes never mix, and so you would never really thermalize if you don't have any anharmonicities. But okay. More questions? Yeah. How much time do I have? I started a bit late, and I'm usually bad with time. So can you?
We have time, so
So let me continue. You need to control me. I can.
There's about 15 or so minutes, but there's a 5-minute leverage. So 15, 20 minutes, it's fine. Okay,
so particle physics. Well, the basic idea how quantum fields emerge in particle physics is really how fields emerge. First, let's talk about fields.
Sorry, João, there's a question in the chat from Pablo. Don't think he can ask, so I'll just read it on your behalf. So Pablo says, sorry if this is basic. In the example, by plugging in a plus a dagger to the power 4th in the diagonalization, will this yield the selection rules of the anharmonic oscillator?
What do you mean selection rules? Sorry,
I don't know.
In terms of like parity, that for example the odd eigenfunctions and the even eigenfunctions do not mix because x to the 4 is even, preserves parity. Is that what it means, or?
Don't know if Pablo wants to clarify. You should be able to unmute. If not, just write in the chat.
Yeah, I meant the like how the oscillator is gonna behave. So I haven't taken quantum, so I'm kind of like learning on the spot. But like how the odd states, what energy states the oscillator is like allowed to go to.
You mean in real time?
Yeah.
Okay. So this is, it's a slightly different question. Okay, so let me show you here the picture. Where is it? Here, this picture, right? So the harmonic oscillator has these states, n equals 0, 1, 2, this discrete level of states. And now one thing you may ask is to say, let me say I prepare the system in one state, like, I don't know, n equals 2. And if it was harmonic, it will stay there forever, right? That's what's called a stationary state. It just stays there forever.
Yeah.
But if you have a small anharmonicity, the system will start to mix, will jump from some states to the others, right? It will start mixing, evolve in time, because now this state n equals 2 is an eigenstate of the harmonic oscillator, but not of the anharmonic oscillator. Okay, so this is a question about time evolution. And well, generically, with time, it can actually mix with all states as long as it's the same overall symmetry. So okay, it will only mix to the even n states. The odd n don't mix because of this parity.
Oh, okay.
But this is one question about time evolution. What I was solving was a different question, was saying, can I compute the exact stationary states of the anharmonic oscillator? Okay, so once you change the Hamiltonian, you can still ask what are the new eigenstates, and they are different, but they still exist. And I was computing in particular how the energy of the ground state changes as a function of lambda, the deformation, the anharmonicity parameter.
That makes sense. Yeah, thank you.
Okay, thank you for the question. Okay, so let me go to particle physics. So here, particle physics is basically fields appear because special relativity doesn't allow action at a distance. Okay, and here I actually made a few pictures which should be understandable by the beginners. So it might bore the advanced students. So I'll try to go fast unless you ask me questions. Okay. Okay, so here I have two people, Bob and Alice. Okay, so Bob is standing still in his position, and Alice is passing by with a rocket. Okay, flying in a rocket. Don't be confused. You see, Alice likes to wear short hair, but Bob likes dead metal and black hair, long black hair. Okay, that's So now the important point that I want to use in this picture is what is equal time events for Bob and what is equal time for Alice, right? And well, the advanced students know very well, this one is obvious. So let's say the time of Bob being 0 is this horizontal black line. And there is a very algorithmic way to check that, okay, at least in principle. So what Bob can do is to say, well, I want to know what are the space points that are at t equals 0 for me. So what should I do? Well, I can, let's say, I don't know, at some time, let's say minus t0, I emit some light. Okay, so I make a flash and some photons are emitted. And then I detect, okay, and this flash goes and reflects from a mirror and comes back exactly at time t0, okay? So if this happens, then Bob says the point of reflection on the mirror has t equals 0 in my reference frame, okay? So, I mean, that happens to both sides, right? Both sides have t equals 0. So that's if you want a algorithmic way to define what is t equals 0 for Bob. You can always check, does this point has t equals 0? Well, let me send a photon at some negative time and receive it exactly at the same positive time t0. And if it reflects at that point, then it is. Okay. Well, of course, here I'm doing the usual trick that I'm representing time, let's say times the speed of light, such that so that photons always travel at 45 degrees, right? Because if they move 1 second vertically times the speed of light, that's exactly the length they move in space. So the trajectory of the photon will be at 45 degrees here. Okay, so this is, well, special relativity 101. Okay? And from this exactly the same argument, Alice can conclude that the surface that has time equals 0 for her is a different surface. Okay, so that's one of the most important things in special relativity. And well, I think I drew the picture here. So of course you can do the same game of emitting light, and these points are exactly the points where, so the points on the blue t equals 0 or, line are the points or the reflection on the mirrors. Okay. So I mean, I think this is basic to most of you. If there is any question from some beginner, we can spend a minute clarifying, but otherwise I'll move on. Okay, perfect. So then this is also clear. Now, if I have two events that happen, okay, for me it's convenient to put them in this region. So I have here the event chicken, and here the event egg. Okay, so something that happened at this position in space and at this moment in time. Then Bob and Alice are going to disagree, right? Because Bob says, well, the egg is first, it has negative time, and the chicken has positive time, is after t equals 0. But Alice is the opposite, right? Alice is the chicken with negative time before t equals 0, and the egg after t equals 0. So Alice says chicken before the egg. Okay, so this is the basic principle of relativity of simultaneity that Einstein discovered, and therefore the chicken and the egg cannot influence each other. Okay, so we immediately know that, for example, the law of gravitation of Newton cannot be correct. Right? We cannot feel a force that is just the product of the masses divided by the distance instantaneously, because if we move the sun, imagine there was some explosion in the sun, so the mass of the sun would be displaced, and we would immediately feel that that the force changed on Earth because, well, the position of the sun changed. This would be incompatible with relativity, because for some observer, actually, we would feel the force changing before the explosion happened, right? What happens before and after depends on the observer for things that are what's called space-like separated, like the egg and the chicken in this picture. Okay, so the solution to this is well known and was already worked in electromagnetism, for example. The solution is to introduce fields. So fields carry the information of any change in, say, the mass distribution or the charge distribution at a finite velocity. Okay, so when we have a charge and we move the charge, the force on the other charge doesn't change instantaneously. It's just the electric field changes. So there's a wave in the electric field that moves at the speed of light that changes the force, but it takes time, takes the speed of light to get there. Okay, so that's the basic idea, that relativity leads to locality. So you need the interactions to be local and not action at a distance. And the way to represent that in physics is to use fields. Okay. And here I wrote the simplest field theory. I wrote a field, a scalar field, that only depends on one coordinate x and time. Okay, so this is not a full field for like 3+1 dimensions where we live, but it's a good model. It's, for example, you can field this field phi as the height of a string, right? If you have a string on a guitar and you start vibrating it, this is basically the action for the height of the string, if you want, for the displacement of the string, if you call that the field phi. Okay, so this is a trivial example of a theory of quantum field theory, and you can check. Okay, this is perhaps for those of you that already learned it. You can check that this is in fact invariant under Lorentz transformations. Okay, under changes of frame in special relativity. Well, let me not go into these details, but you can check if you want that the action written like that is indeed invariant under Lorentz transformations as it should. So let me just discuss a bit the physics and connect with this harmonic oscillator. Okay, so what we call a free theory is when the potential is quadratic. So the action is quadratic in the time derivatives, the space derivatives, and the field phi itself. And this coefficient is the mass of the particle. But now think of this, what is this really is in terms of degrees of freedom. This is just a system of coupled harmonic oscillators. Okay, so the easiest way to see this is to discretize space. So just take points xj to be some lattice A. Okay, I can draw. Okay, so you take x, and now you take just some discrete j equals, I don't know, 0, 1, -1, 2, this label j, and this distance to be a, and now you just take a discrete set of points instead of the continuum. And so you discretize the derivative, and this is what you get, right? So you get time derivative, the space derivative just becomes this difference, and this is, well, just this mass term. But this clearly is just a set of coupled harmonic oscillators, right? Each phi j is one harmonic oscillator, and they are coupled by this term, right? Because it couples the phi j with phi j plus 1. But harmonic oscillators, even if they are coupled, if they are all harmonic, so if the thing, the action is fully quadratic, we know how to solve. Okay, so this is like a system of masses coupled by springs. So we know how to solve this. We just go to normal modes. Okay, so this is the expansion in normal modes. This is what you will see in your quantum field theory 1. Is nothing more than the expansion in normal modes of the theory. And yeah, okay. So, well, I don't want to go too much into the details. I just want to make this point that then if you do quantum mechanics, what you get is that the Hamiltonian is exactly the same as the Hamiltonian for the harmonic oscillator, A dagger A. Okay, the plus a half is a problem because if you get, there's an infinite number of modes. There's one mode for each Fourier component, so for each momentum k, and you're integrating over k. And each mode has a frequency that depends on k via this standard relativistic dispersion relation, that the energy squared is the momentum squared plus the mass squared. Okay, so that's really simple. If quantum mechanics was just, if quantum field theory was just that, it's solved. It's exactly solvable. The only issue here is that you get a divergent vacuum energy because each harmonic oscillator contributes a half, and you have infinite number of them, and so they this sum diverges. But the ground state energy, the vacuum energy, is not observable, right? We only observe excitations, how to excite the vacuum and how these excitations decay. The vacuum is just some reference frame, reference value of the energy, so we can completely forget that to do particle physics. Well, I should say this is not true for gravity. So if you have gravity, the vacuum energy does affect the dynamics. In particular, it creates expanded evolution, and that's one of the main problems in physics, in theoretical physics, is to understand why the observed expansion of the universe is so small compared with our calculation based on the vacuum energy of the quantum fields we know exist. Okay, so this is, but we're not going to discuss this today. Okay, so that's it. That would be extremely simple. But of course, the world is more interesting, so there are interactions. So for example, if the potential for the field is not just quadratic, for example, it has here a lambda phi to the 4, then what you get is again an infinite set of oscillators, but now they are anharmonic. Okay, and now you also don't know how to solve it, like in quantum mechanics. So the natural thing to do is to do perturbation theory, and this is what Feynman diagrams are. Okay, so Feynman diagrams are way, a smart way to do perturbation theory for an infinite system of coupled and harmonic oscillators. Okay, so unfortunately, we don't know the analog of this Bender and Wu recursion relations, because I think it's just very complicated because they are infinite number of coupled oscillators, so we cannot just generalize it easily. So let me just tell you the pictures that you see everywhere. So I just want to explain you the logic. So for example, suppose you want to compute some specific observable, take a scattering amplitude, like the probability of two particles scattering to two particles at some angle, let's say, some specific observable. It's not very important. So in the free theory, when lambda is 0, they just go through, they don't interact. But then to first order in lambda, they can interact, and you can, I mean, this diagram tells you that there is a number to compute. There is a one-to-one map between the diagram and some integral that gives a number. And then at order lambda square, okay, you can draw several diagrams, but any diagram is basically some symbol for a number, and so on and so forth. But what I want to emphasize here is that exactly like in quantum mechanics, this series is divergent, okay? So this series can work very well in practice. If lambda is very small, can you keep like a few terms and you get a very high precision result. But it cannot define the theory as a matter of principle, because if you really want arbitrary precision, this sum is just divergent. It does not define the theory. Okay, so it's exactly like in quantum mechanics. And this is a big issue because, well, I already mentioned quantum chromodynamics, so the theory of quarks and gluons. This theory is just strongly coupled, and this perturbation theory just doesn't work, not even in practice, not even, I mean, it's just, so here, this is just useless. And I just want to emphasize that everything we know about particle physics fall into this category, okay? So you have seen this table many times of the fundamental particles. What this actually means is that each particle here, so for each particle, there is a field in the Lagrangian of the standard model. Okay, so each particle has its own field. And this is, if you go to CERN, you can buy this t-shirt. So you can, this is the Lagrangian of the standard model. So you see here, this psi represents, I mean, the fermions, like the electrons and the quarks, and the phi represents the Higgs boson. And this F mu nu represents the photon or the gluons, all the gauge bosons, okay? So, and all, well, essentially all the computations we do to reproduce the experiments in colliders are done using perturbation theory, okay? So they, by construction, they are inherently just an approximation that really does not mathematically define the theory entirely. So that's the status. And well, I guess I'm really running out of time. So maybe I will finish here or something. Maybe I'll skip the next part. Maybe I'll finish here. If, well, I can answer more questions or tell you more stuff. I had a bit more to say, but I think this is a good point to summarize. So we saw two complementary perspectives over quantum field theory. So one was to take this continuum limit of lattice models. And this is extremely useful, and it's non-perturbative. This is actually a definition that you can work at finite lambda. We saw in practice how this Hamiltonian truncation, so I include Hamiltonian truncation here because truncating the number of states is more or less equivalent to making a lattice, okay? Because you're like truncating in energy is equivalent to truncating in distances. You don't allow very high energies. It means you don't allow very short distances. Okay, so it's the same type of philosophy. And then there is another approach which is always to consider the quantum field theory directly in the continuum, okay? That they exist as an object in the continuum. And this is, if you want, a more mathematical approach to quantum field theories that we've been working on for the past few years. And I like to make this analogy. So here I drew you this picture. So this is a circle. And this is a circle for Archimedes. Okay. So Archimedes, more than 2,000 years ago, proved that, well, whatever, the area of the circle divided by the square that has side equal to the radius, right? That's pi, that's the definition of pi. He proved upper and lower bound to pi doing these approximations, right? Approximating the circle by a regular polygon that is inside the circle and by another one that is outside. So that allows you to construct an upper and lower bound to pi. I really recommend that you go and read this. I mean, we can read the original works of Archimedes. They are available online. You can just go to Wikipedia and there's some link there. And you can really read this super modern way of thinking, of drawing these geometries. It's quite remarkable that more than 2,000 years ago, there was such a modern mathematical way of thinking already. Okay, so we have a long history of science that sometimes we don't remember. Okay, so I think the most developed approach nowadays is this one, and it works very well in practice. The work for the future and the ongoing work is to try to come up with a mathematical definition that works directly in the continuum, okay? Okay, I say here, this is probably too advanced for you, Lie algebras and finite groups. Maybe some of you know this. Okay, so in math, there is an analogous classification of objects that was successful in the 20th century. And I think the 21st century is a good century to actually classify the full space of consistent quantum field theories. And okay, let me skip. I had a few more things to say, but I think in view of time, let me just conclude here and answer questions that you may have. Thank you very much.
Great, thank you. Yeah, I open the floor for any questions people may have. So I think you should be able to unmute yourself and ask your question. If not, just write them in the chat and I can read them.
I got a question about how you said that every particle in the standard model has like its own field, like in the Lagrangian. Could you explain a bit more about that?
Yes, so the notion of particle is what is a particle? Yeah, perhaps I could have emphasized that more. So a particle is just an excitation of the field. So for example, I don't know, let me try to be concrete. So perhaps the system you know better is the string of a guitar, that you have waves.
Yeah.
And you can do normal modes, right? There is like the sine and then the one with one node and the two nodes, okay? So you know that system, right?
Yeah.
So now, each one of the normal modes is like an harmonic oscillator, okay? Because I mean, each mode just vibrates at a constant frequency. That's a note, right? That's why we hear that in music. It's a specific frequency. So each harmonic oscillator now can be excited, right? Can be in the ground, in quantum mechanics. Now it can be in the ground state or can be in the first excited state or second. So this number n of the excitation you put in a given mode is a particle. If you put n excitations, you put n particles. This is what a particle is, okay? And then you have several modes, so each mode corresponds to one wavelength. So if you put a particle in a given mode, you put a particle of a given wavelength. But okay, now it depends if they are bosons or they are fermions, but okay, if they are bosons, like the waves on a string, you can put many modes, so you can put many particles in the same wavelength. And this is exactly the same that we do in a laser. So in a laser, we have some cavity between two mirrors, and we have normal modes of the electromagnetic field. And in a mode, you can put many, many particles. So you put many photons in the same mode. That means that's a laser, yeah. So a laser is just many photons. So photon is the particle, is just the excitation level you put in a given vibration mode. Okay, so this, if everything was harmonic, you just make a photon and it lives forever and never interacts with anything else. So, okay, life would be extremely boring. But actually, the world is anharmonic, so particles can interact. So the photon propagates, but at some time it can, for example, I mean, you probably have seen pictures like that, for example, you have an electron, let's say 2 electrons, and let's say this is time. So you send one against the other, and well, they should repel, they are electrons. Well, fundamentally what happens is that this electron emits a photon that is absorbed by the other one. And so the electrons repel because they exchange photons. And so this diagram, I mean, gives you an idea of the microscopic process that is happening. But I mean, mathematically, what this diagram means, you're computing the first order in perturbation theory to the interaction between electrons. I hope I answered your question, but did I?
So the particles are just like a manifestation of the waves?
Yes.
Okay.
The particles are a quantization of the waves. So the waves in classical mechanics can have any amplitude. In quantum mechanics, they are discretized just by, well, like any energy levels of any system in quantum mechanics. And this discretization is the particle number. 1 particle, 2 particles, 3 particles, and that's it.
And then you write the Lagrangian of those waves and you get the standard model?
Yes.
Okay, okay, thank you.
In particular, say the first term here, well, it's written in a way that I guess you still don't recognize, but the first term, the first line is just Maxwell, is the Lagrangian that gives electromagnetism, the Maxwell equations, this F mu nu, F mu nu. So that's one term. It tells you how the photon propagates.
Wow, okay, thank you.
Okay.
Any more questions?
Yeah, I would have a question.
Sure, go ahead.
Yeah, so this is the Lagrangian of a standard model, you know. So, and I was wondering, when you consider effective field theories, you add on to these Lagrangian specific parts, or you define couplings in a different way, or you add couplings or whatever. You have plenty of options to deal with. So, is there any Lagrangian for the standard model which would simplify the expression we have right now there, in terms of if we introduce effective field theories, like, and then do something like a grand unified theory, would this in any case shorten up this Lagrangian, because it's pretty long and has a lot of expressions standing for the different interactions in the universe, but could like general like grand unified theory just shorten up the terms, including like strong force into electroweak, for example?
I mean, that's the idea of unification, right? Unification is precisely the idea that, well, let me give you the example that you know, right? The example of electromagnetism, right? Maxwell was the first unificator, right? So before you had the electric field and magnetic field, these were separate things. They were not connected, and moreover, they were not connected to light, right? There were people doing experiments with measuring forces between charges, and people, Faraday was playing with currents in some circuits, in magnets. And then Maxwell put everything together, and he actually found out that if you really put everything together and make the equations consistent, you predict that there are waves, and these waves propagate very fast at a speed compatible with the observed speed of light at that time.
Yeah, so, but I was just wondering, so for example,
let me just conclude. So
okay.
Before you had like two effects, and then Maxwell put it all together in one field called the electromagnetic field, which is the first line. So the first line here, F mu nu, encodes both the electric and magnetic field, and it's just one small term in this Lagrangian, F mu nu, F mu nu.
Yeah, I know.
So
but
now the idea of grandification is that you can do the same, that you can say, actually, the quarks and say the electron are not separate particles. They are part of a bigger particle, what we call a multiplet of a bigger symmetry, like SU5 or SO10, and maybe you heard these words.
Yeah, but SU5 is already out, right? Because it doesn't work in the end.
So I'm not sure what you're asking. I mean, the idea of unification is that you will write a smaller Lagrangian because the fields that you write will codify many particles at the same time. Now, of course, it has to work with experiment, right? It has to be compatible with nature. And so far, we have not found a way of unifying that is compatible with experiment. So
yeah, but in any way, it wouldn't never shorten up this Lagrangian, because thinking about electroweak symmetry breaking, you know, here we have a term for electromagnetism, and electroweak is the force we combined, where you combined electromagnetism with the weak force. So, but we still have a term for electromagnetism and a term for the weak force in there.
Well, so not necessarily. The way it is written, actually, this F mu nu, you can think of it as that is a field for the full, whatever, SU2 cross U1.
Yeah, but isn't this the Lagrangian after the symmetry breaking and not in the on the symmetry breaking?
Actually, I think in this picture, it's before symmetry breaking, right? Because there's still d phi, v of phi. So
yeah, sure. Yeah, right.
So, okay, I mean, okay, this is a bit technical, but you
it's
can have,
interesting.
It's true, you can have, right, so very good. It's like saying, the question is, you can have a very simple Lagrangian and still the world be complicated because of spontaneous symmetry breaking, right? So there is this idea that the Maxwell's equations are simple, right? But you can have, well, let's say, I don't know, very complicated objects like a dog. And basically a dog is just ruled by Maxwell equations, right? It's just interaction between electromagnetic forces between the particles that puts the dog together, right? But the dog doesn't have all the symmetries of Maxwell equations. It's one specific solution. So that's the idea, that you can have a Lagrangian which is very, very symmetric. And then the world is more complicated. I mean, we have like electron that has different mass than the quarks and the neutrinos and all that. But that's just because there was some spontaneous symmetry breaking. So it happens that the state we live in, the part of the universe we live in, broke some symmetries, and then the world looks a bit more messy, like whatever, a chair or something is not as symmetric as Maxwell equations. So, I mean, but of course you cannot remove the complexity from the world. The fact that the electron has different mass from the neutrino, it's true. So if you put them in a multiplet, there must be some spontaneous symmetry breaking to justify that then in the end they look different, right? So depends what you prefer. We physicists prefer to make the fundamental equations as clean as possible, as symmetric as possible, and then explain the complexity of the world as some kind of just a specific state that doesn't have the full symmetry.
So the very short answer would be no for the question, because in the end, it will always be complicated, no matter how short your term is. We'll just like express in the end in very complicated specific solutions.
Yeah, the same way that if you want to describe DNA or proteins, it's complicated, although the fundamental physics is simple.
Yeah, I was just wondering whether you can come up with the term like in the theory, then making this complex solutions way more easier to describe in the end. So this is what I was thinking about. If you implement this in GUT, then it would just not be much shorter Lagrangian, just like two terms less, but it would be easier to describe. Sometimes, you know, physicists find out a new method to describe new old phenomena in a completely different way. But you know, it's pretty difficult and it's pretty technical. I don't know, but yeah, in the end, thanks for the answer and thanks for the short discussion.
Thank you.
Thanks. Any more questions? If not, I have a very quick one. Again, experimental, in case you want to comment. Very recently, a month ago or so, we had the preliminary results from the Muon G2 experiment. I was just wondering if you wanted to comment what that's. It's not a discovery yet, but it's hinting at it. And what would it mean for theory? What theory says about that?
Yeah, so I mean, I'm not a specialist on that, but let me tell you just briefly. So for those of you that don't know, so there is some experiment that measures the gyromagnetic effect, or whatever, the ratio of magnetic moment to the spin of the muon. And it's very precise, so it measures it with many digits. I can't remember how many, but 8 digits or 6 digits, something like that.
Something like that, yeah.
And so it's a challenge for theory to match that, right? Because it's a very high precise measurement. So can the standard model predict that number? And there is some confusion. So apparently the predictions that were published from the standard model were also very precise, but they differ, okay? So they differ, whatever, maybe, I'm not sure if it's 3 standard deviations by now or something.
It's 4 sigma.
It's already 4 standard deviations from the experimental value.
Yeah.
So now there's a controversy. Is there something missing in the standard model, or is the computation wrong, okay? Well, I don't know the answer, but I think we should give some time, because this computation is really non-trivial. You see, it's exactly what I'm describing here. You need to sum many orders of perturbation theory like here, and then there are some effects that come from quarks and gluons, which are extremely difficult to do in perturbation theory. There are 2 ways of doing it. One is like to measure other things in accelerators and then use those measurements indirectly to compute this, or to use exactly the approach of statistical mechanics to do lattice Monte Carlo simulations to measure those things, because perturbation theory does not work. And there are other groups that actually did lattice simulations, and they get the result more compatible with the experiment. So I think there's still a lot of controversy. I think now the ball is on the side of theory to clean up their mess and decide which value we actually think is the prediction of the standard model. But that's a very non-trivial challenge. So I don't know, might take months or a few years to really make sure we know how to compute this number.
Yeah.
Can I add a little question on that?
Yeah, sure.
So João, do you know if these people doing like really precise perturbation theory, do they just directly sum it? I mean, coupling is small, so it's good to just resum it. But do they do Borel summations, or they just actually do the sum?
Honestly, I don't know the details, but I would think that for like electromagnetic effects, you can just sum, because the coupling is so small that to the order you go, right? Like maybe they go to 4 loops or something. You're still summing very small number. The series will only start to grow, I don't know, at 50 loops or something. So, but the real challenge is the hadronic effects, the quark and gluon effects that also appear in this computation if you want to do it so precisely. Although it's a muon, you see, we're computing something for the muon, but in quantum field theory, everything that is possible can happen. So the muon can interact with like a pair of quark anti-quark that is created from the vacuum, and then it's annihilated again. And it's that kind of processes that are very hard to compute. And these ones, at least the sub part of the computation that comes from this, they cannot use perturbation theory.
I see.
Okay, thank you. Are there any other questions? If not, I think we can finish here. Thank you again, João, for accepting our invitation to be here today. And I hope everyone enjoyed I think it was a very interesting presentation, and I think hopefully most people were able to follow it. I'll just say, if you want to send a mathematical workbook, we can then give it to the participants. Yeah, thank you.
Thank you very much. It was a pleasure. Enjoy the rest of the program.
Okay.
Bye.
Thank you. Bye. I don't know if DOC wants to say something now. If you're there. If not, I think we can finish here. They don't seem to be there. Well, okay.
Hi.
Oh, there they are.
Hi, Pedro.
Hello. I was just wondering if you wanted to say anything, or
no, just thank you,
okay.
João. Just thank everybody.
Thank you.
Okay then. Thank you. Bye.
Thank you, guys.